number 15 is a nice problem that involves the superposition of magnetic fields due to two current-carrying wires. So in this particular problem here, there's a wire up here that has a current coming straight out at the camera, straight out up like that. That's what the dot means, and then the cross here means that there's another wire here with the current going straight down into the page. So there's two wires like that, and what the problem wants to know then is what is the magnetic field at points 1, 2, and 3 because of these current-carrying wires. And incidentally, each one of these wires here is 1 centimeter above the axis. Okay, 1 centimeter there and 1 centimeter here. That's sort of the relative orientation there. So this is a problem that if you're kind of careful here, you can sort of see what happens. Now, we know we have something called the right-hand rule that says if you hold your thumb in the direction of current and curl it around a wire, that'll give you the direction of the magnetic field. So for this wire here, there's a magnetic field circulating around it like this. For this wire here, because it's going into the page, there's a magnetic field circulating around this wire like that. So what I'm going to do is sort of draw that magnetic field at point 1 and these points here and see if we can sort of figure out what our answer is going to be. So because of this top wire here, this green one right here, I guess I've drawn them both green here, there's going to be a big circulating magnetic field going counterclockwise around it, and one of the circles will go through point 1. So something like this. I'll just draw it as carefully as I can. It'll be a big circle. It should be centered about that wire here going through there, but in either case at point 1 here, there's a magnetic field going through point 1 because of this wire that looks like this. Okay? Now if you do the same sort of analysis for this wire here, well, this is going to be a clockwise rotation, clockwise sort of circulating magnetic field, if you will, which will sort of look like this through point 1. It's going to go around like this, around like that. And it'll go through point 1 and come around and look just like this. My circle is terrible, I know, but it's a circle like that. So there'll be a magnetic field right through this point pointing that way. So if we label these two arrows here, this one is the magnetic field due to the top wire, and this one right here is the magnetic field due to the bottom wire. Okay, so you have both of those sort of in there, top and bottom. So if I take these two vectors and sort of remove them from the problem so we can look at them clearly, not with my messy circle, I'll get a magnetic field up this way, a magnetic field down that way, and once again, if I label the origin of these arrows here, this is B due to the bottom wire, this is B to the top wire. The total B field then is going to be the vector sum of these things, which is going to be one like this. I'll call it B1, meaning the total magnetic field at point 1. This is the problem now that I need to focus on. And using the result we have for the magnetic field outside of a current-carrying wire, I think you can use that to sort of nail down some of the results. In particular, we know that the magnetic field outside of a current-carrying wire here is mu naught times I over 2 pi times d, where d is the distance from the wire and I is the current in the wire. Now the problem gives you the current traveling through the wire there. I believe in this particular problem, the current is 10 amps in each wire. So you know what I is here. I is going to be 10 amps in each wire. And now what you need to do is a bit of geometry to figure out, well, how far is point 1, for instance, from the wire. So in this particular problem here, point 1 is this far from the wire here. So if this is 1 centimeter right here, and that's 1 centimeter right there, I believe that's what the problem calls for. Yes, it is 1 centimeter. Then you can figure out this distance from the Pythagorean theorem here. This distance here is the square root of 1 squared plus 1 squared, and I'll be cautioning you here, that is in centimeters. Make sure you convert that to meters before you go doing any more calculations with it. But that would be the d here that goes into this form for calculating, say, what b top is right here. So in other words, I'm telling you here that b top here is something like mu naught times 10 over 2 pi times this d here, which is the square root of 1 squared plus 1 squared, but I'm going to circle it. You're not quite ready to compute on it. You need to make sure this is going to be in meters before you proceed with that calculation to stick it all in the SI units. That's what B top would be. Okay, so to continue with the problem then, you do the exact same thing, but for the bottom wire now. So the bottom wire is sitting down here. Here's the distance between the bottom wire and the point in question right here, and you can figure that out. I think it's going to be the same number as it is for the top wire, so you can figure out the magnetic field due to the bottom wire, which is the magnitude of this particular arrow right here. When you have that all done, you've got it reduced down to a vector addition problem now. You can figure out what this angle is right here. I believe it's going to be 45 degrees. You can figure out what that angle is right there. And it looks like the y components are going to cancel. There is going to be an x component. And so for this particular one here, I get that B1 is going to be 2 times 10 to the minus 4 Tesla. That would be the magnetic field at point 1. Now there's 2 more points in question. There's actually quite a bit of work here you have to do to figure out what it is at 1, but there's also a magnetic field at point 2 as well. Now point 2 is a particular case where if you use the right-hand rule again, I can come back here again and see that the magnetic field direction doesn't change. It's sort of going this way for the top wire, and I think it's going, if I put the arrows on here, going this way for that bottom wire circulating around according to the right-hand rule. But now I just need to come in here and figure out what it is for this point. So if I put my thumb in the direction of current for this wire and curl my hands around, I'll get a magnetic field due to the top wire going that way. And you can label that B top, right through that point. If I do the same thing for the bottom wire, thumb in the direction of current, curl around this way, I'll get a magnetic field going this way for the bottom wire. Label that B bottom. So again, if I take these two arrows here and sort of get out of the problem so I can sort of analyze what I'm doing here, I have a B bottom here and a B top right here, and it's very straightforward to do a superposition to see what that's going to be, but I will get a net magnetic field this way, which will just be the sum of the two. How do you find what B bottom and B top are? Return back to the formula for the magnetic field outside of a current carrying wire. I don't have this diagonal anymore. It's a mu naught. The current's the same, 10 amps, 2 pi times D, where for point 2, D is just this distance right here, and this distance right here for the lower wire. I believe it's going to be 1 centimeter. So you can figure out what B bottom and B top are to figure out what you need to put into this equation here to get that B2 here is B bottom plus B top, something like that. And the answer I got for B2 is 4 times 10 to the minus 4 Tesla. Nice superposition problem there. Okay? The very last one is to find the magnetic field out here at point 3, out there. This is going to be a very similar problem to point 1 in that this magnetic field still circulates around like this, and so you can imagine, like if I can just go back to the drawing here, as this magnetic field circulates around, at this point, the top wire is going to present a magnetic field like that, and this is just part of a larger circle. Now I know I'm going to mess this up by drawing it, but of a larger circle that sort of spins around the top wire and looks like that, but I've tried to preserve the orientation. This area should be tangential to the circle, which it almost is, but my drawing is going degrading very quickly, isn't it? You can draw the same thing for this circle here. It's going to be a clockwise circle that goes around like that, same point in here, but it's going to sort of go around like this, almost the same diameter as the red one. There'll be an arrow right there due to this bottom wire, B bottom, like that. So there's the B top and the B bottom for this particular wire. So it looks like you're in exactly the same situation as the top, in that the magnetic field at point 3 will come from a figure that looks exactly like the one for number 1. In fact, the answer is even the same. This answer is the same for points 1 and 3 because there's symmetry points about the wire there, so you get your answer that way. So it's very important in this problem here to use the right-hand rule, select each one of these points here, and come up with a little figure here that shows what the magnetic field is, not in the entire region around the whole problem, but at every one of these individual points. Get a bit of 2D vector addition at this point and this point here, at the midpoint right here. Both magnetic field lines are along the x-axis, so the superposition is much easier, but it's still up to you to use the right-hand rule and understanding these circular magnetic fields around wires to even construct a figure like this one or like this one to begin with. So there you go.